Hi, thanks for joining us today. We're going to be talking about lesson 7-4, which is a review of everything you need to know about logarithms from this point forward. As I said in the video for 7-1, one of the reasons we're going to go over this stuff is you're going to see these functions more and more on the non-calculator portion. You have to know how to do everything we're doing today without a calculator. We will use the calculator at some points during the video, but only to motivate other ideas. Again, make sure you understand everything in this video before proceeding further. The reason we're going over this is so that we can know how to do calculus on these functions, where certain techniques covered here will be necessary. In this video, we're just going to be covering the basics. Let's begin. Since f e to the x is one-to-one, continuous and increasing, monotonic would have been the word we used from previous video, 7-3. It must have an inverse. Again, 7-3. Monotonic, inverse, one-to-one. All of these are the same thing. Monotonic means increasing or decreasing. However, if you switch x and y in the equation, that's how we normally get inverses, this would become this. And there's no way to isolate y using algebraic methods. So instead we define an inverse function, and this is how it's done naturally, mathematically. We define the inverse function for this guy. So this inverse function will be called the natural logarithmic function. Because e is somewhat natural, so its inverse function, the logarithm that undoes it, is also natural. And we'll call it natural log, ln. The reason it goes ln instead of nl, that's what students always ask me, is because it's from the French, logarithm natural or something. So, x equals e to the y equals ln x. That's the idea. So if we have a general exponential function, a to the x, its inverse would be log base a. This is called the base. I would call this the input, log for logarithm. So log base e, that's what natural log is. Natural log is log base e. Log base 10 is the most common log besides log base e, and so we'll often drop the base there. Almost all the logs you see in this course will be natural. Not today. All right. So I'm going to put example 1 before the box, if you're looking at the notes. Use a calculator to graph these two functions in the same coordinate plane. So we're going to go to y equals on our graphing calculator. Pause the video if you need to get it out. We're going to put natural log in for y1. Natural log is this button right above store of x. We'll close the parentheses just to be nice. And here we're just going to use the button above that, log. If you write log, the calculator thinks it's log base 10. If you write natural log, the calculator thinks it's natural log base e. Zoom 6. It's way too fast. I don't know. I was complaining about the old emulator, but this one's way too good. So one more time, zoom 6. So in blue we have log base e, or natural log, and in red we have log base 10, or just log. It's also known as Briggs logarithm. So, what similarities do we notice here? Well, one thing to notice for sure is your calculator's inability to accurately graph what's going on here. They both share a vertical asymptote at the y-axis. The y-axis is a vertical asymptote for both, and because of your calculator's method of graphing, your calculator, as we've said all year, does a very poor job of showing that asymptote. So the graphs just kind of stop. You have to use your knowledge of graphs, your knowledge of these functions to know they're continuous and would go on forever toward the asymptote, never quite crossing it. They both do not appear in quadrants 2 or 3. Quadrant 2 up here, quadrant 3 down here. So their domain is only 0, not including, to infinity. I said already they're both continuous. They have a similar shape, which is a concave down shape. They're both increasing. They're both always increasing. And I think that's everything. So those are the similarities we're going to look at. And those are the similarities you're going to be asked to memorize. And the main reason, again, for all of this is so you can answer questions. So you can answer questions like, so if the domain is there, that you would know that log of 0 is undefined. Okay? If someone asks you to input log, that's a problem point. The problem, the domain of log causes a lot of problems for things we want to do. Like talk about its number line, right? You have to know domain for number line purposes. Continuous means we can do lots of useful things. Increasing, that'll be interesting about its derivative when we get there. Concave downward, we mentioned that. 1-to-1 has an inverse function. It's always increasing, so it's always monotonic. It's monotonic. Monotonic means it passes the horizontal line test. It means it has an inverse. It is an inverse. Its inverse would be a to the x. Inverse is a to the x, right? Just like a to the x's inverse is log. They're mutual. The y-axis is a vertical asymptote. As I get close to 0, the graph goes down toward negative infinity. The x-intercept is 1, 0. Another key point is a, 1. And we can compare all of these properties to these facts. Notice how they're exactly backwards of these facts on page 135 in your book. Domain is 0 to infinity. Range is all real numbers. Domain is all real numbers. Range is 0 to infinity. The graph is continuous, increasing concave down for log. For E, the graph is continuous, increasing concave up. So match for increasing, and reverse for concavity. You don't have to memorize that they're reversed, but if you feel like, oh God, I'm memorizing so much, you can do most of this stuff just remembering log. The y-axis is a vertical asymptote. The x-axis is a horizontal asymptote. X-intercept is 1, 0. Y-intercept is 0, 1 for E. Okay? So we can learn how to graph most of this stuff by hand without using a calculator. Let's try to sketch a graph. As I talked about before, many times, we're going to start by looking at, in red, y equals, we're going to work for inside out. Try to graph this. Try to graph a beginner option. Try to graph this. We're going to use a dotted line because we're going to end up having to transform it again. Let's see what you get. 3, 2, 1. Did you draw something? Did you really? So I hope you noticed it was a shift. Subtraction by 2 on the inside would be a shift by 2 to the right. So if you got it to shift 2 to the right, very good. Our old guy, natural log, like we just talked about on this graph, and in the table, has an x-intercept at 1, 0. So our new guy shifting 2 to the right should have an intercept at 3, 0. Okay. The vertical asymptote shifts. All the x stuff's shifting too. The vertical asymptote used to be on the y-axis, so it shifts over by 2 also. And what we get I don't like that. What we get is that. We'll have a concave down guy that increases and hits that key point. Okay? It has a vertical asymptote. Now, let's think about this. What do the absolute value bars do in particular? Did you transform this dotted line? 3, 2, 1. What the absolute value does is transform everything below the x-axis and reflects that above the x-axis. Anything that's already above the x-axis, all the parts with already a positive y-coordinate stay the same. All this stuff flips. Now when it flips, its shape changes to concave up. And that's something that's a little useful to know, not wholly necessary. I would erase this scratch work if I was on a test. We'll leave it because it's part of our notes. The asymptote is still an asymptote. And this point is very important. What's important about this point? Think about it. Write an answer down. That's a sharp turn now. And as we talked about the whole year, absolute value kind of causes sharp turns. If there's an x-intercept, more specifically, if we cross the x-axis, absolute value will make a sharp turn there. If we cross the x-axis on the original graph, the absolute value version will make it into a sharp turn. Just because it's a very unnatural thing. It just breaks that. It just snaps that, flips it up. Okay? I don't know why I did that. All right. Exponential to logarithm form. Some teachers teach a BAP method with base, answer, power. If you understand what that means, great. Otherwise, this is not that hard. So, one thing to notice is that anytime I have an equation arranged in exponential form, I can transform it to an equivalent equation in log form. And you should write equals log base e. That might help you out if you're just getting reused to these problems. So, anytime I have something in log form, I can transform it into an exponential form. And this is the key to many ideas. This works for any base. Again, a is just some number. We're thinking of everything as numbers at this point. So go ahead and change these following equations from an exponential form to logarithm, or vice versa. You should try to change the exponential ones to logarithms and the logarithm 1 to an exponential. 3, 2, 1. So there's 3 parts here. We have a base, which is 3. We have the power, which is an input. And I would say we have an output, or the answer here, 81. So this will become log. The base of the exponent will become the base of my logarithm. The output of my exponent becomes the input, log base 3 of 81. And the input becomes the power. Okay? And this is why some students call it BAP, base, answer, power. If you don't have to think about it like that, the input and the output switch places. The output was 81, now it's the input. The input was 4, the output is now 4. The base is the base. Try this one. If you didn't get that before, try this one. Try the same idea. 3, 2, 1. The base here is E. The input was 0. The output was 1. So log base E of 1 equals, well, I'm sorry, spoilers, equals the output, or sorry, the original input of 0. And the more natural way to write it, this will usually get full credit, would be natural log. That's what that means. Okay? And by the way, just so you're clear, all of these are true statements. Any e to any power is 1. Log of 1 is 0. 3 to the 4th is 81. Log base 3 of 81 is 4. All right, now this one's a little harder. Go backwards. It's the reverse of what we just did. Still about finding the base. And reversing input output. 3, 2, 1. The key idea here, pause the video if you haven't done it yet, is to realize that log, without a base written there, is log base 10. Okay? So that's the base. So my base is 10. The old output is now the input, just like over here and over here. And the old input is now the output. You can check if this is true. You can check if this is true. What's 10 to the negative 1 power? Quick, quick, quick. You should be able to do it. 3, 2, 1. 1/10 equals 0.1. And that's true. Okay? So if you're quick with this stuff, you should always be able to verify that something you write is true. We're beyond that now. This is a review of your pre-calc. So you need to be able to do this. You need to be able to do this well. If you need to borrow a book, if you need some practice exercises, please let me know. Khan has great videos on this. There's lots of good resources. Let me know if you are completely unfamiliar with this. Here we go. Because now we have to use this to figure out some stuff. So, like we had in example 3b, if e to the 0 is 1, natural log of 1 is 0. Since e to the 1 is e, the base was e, the input was 1, the output was e, natural log covers the base, right? That's log base e, is natural log. The old output is the new input, so the old input is the new output. These two facts you need to memorize. You need to memorize, and by memorize I mean if I say, what's natural log of 1, you need to be able to say it's 0 in less than a second. Similarly, if I say natural log of e, you need to be able to say it's 1 in less than a second. The idea, what this is getting at, because you could reverse these, because they're inverses, natural log of e to the n is the same as e to the natural log, and you could write it as they're canceling out. I don't particularly like that. That leads to some sloppy work, but that's just n. And we can check that that's true, right? So let's take this side. Let's write this logarithm equation into exponential form. Now this is going to look weird. Our old base, sorry, we always did that one in red. Our old base is our new base. Our old output over here is our new input. I know that's hard to see. Now to think about. And our old input is our new output. So these two things are equal. But as we talked about in 7-1, if two guys with the same base are equal, it must mean their powers are equal. So e to the natural log n is n. Okay? Now, the main thing we should note, you don't have to be able to prove this, but sometimes seeing a proof helps you remember. I want you to be careful. It needs to look like e to a natural log. E to the natural log x plus 2, so that's the input, is not x plus 2. Okay? A lot of students say, like, oh, those cancel and you're just left with x plus 2. Instead, this side is e to the natural log x times e squared. And now there's nothing else outside the natural log. Now they cancel, but we still have e squared. That's the biggest lie you can tell yourself. And it may not have come up that much in your pre-calculus courses. Chapter 8 will destroy you if you make mistakes like that. Please be careful to write it in this way. Everything has to be gone from the outside of natural log. So, careful, clear, isolate, one way to call it, ln first before cancel. That's my golden advice. Careful, careful. All right, so let's use this inverse idea. Vice versa is true too. Is there anything else with the e? No. So they can cancel out, and this is just root 2. Easy peasy. These ones cancel out. You just have 3x. Log, I've seen lots of students get confused here. Log is log base 10 though. They do cancel out. We're just left with 2. Log base 2 of 2x squared. Just x squared. So that's simple. There's more advanced ones on the homework. I want you to try out 1 through, 1 second, 25, 27, yeah, 1 through 27 on the homework. On page 147 to 148. It seems like a lot. This should be simple. Shake off the dust, everyone, before continuing on. You should try some of these out. You should make sure you get a handle on it, at least on some level. Have a good night. Have a good day. Thanks for watching. Bye.